Yep, it seems to be working. All right, so thanks for coming along. I'm just going to be introducing some of the work I've been doing for my dissertation on looking at Windows memory and how we can use memory forensics techniques to try and find and fix malware infections fairly early on, and a bit earlier on than you might otherwise be able to. It's also going to be looking at fileless malware, where you might not have many other ways of finding it besides behavioral analysis. So yeah, that's the title of my dissertation. If anyone wants to chat to me about it afterwards, I'd be very interested in hearing from anyone who's got industry experience of this. This talk itself is going to be a fairly high-level overview. I've tried not to make it sort of going in depth with Windows debug and code for it. So it's just a fairly high-level overview of these things. So we're looking at what's the point of all this, a bit of introduction to Windows memory management, and then looking at some methods for locating relevant stuff within a computer's memory space. So starting out with what the point, I mean, that's the primary thing, is that fileless malware is up and coming. Over the last 2 or 3 years, we've seen quite an increase in what we call fileless malware. I'll go over that in more detail in a minute if you're not sure what that is. But we're starting to see malware which is only existing in memory. And this, oh, I missed the, there we go. This is a graph from a report by Cowman at the end of 2016. Now, I'm a great believer when you can prove anything with statistics, but I think it's a useful graph anyway, looking at percentage by month of non-malware PowerShell and WMI, or Windows memory instrumentation, management instrumentation, attacks that their customers experienced in 2016. You can see at the start of the year, from around about 3%, it jumped to 12% almost immediately, and has been sort of trending upwards since. So yeah, this benefits your fileless malware, but it also does have applications in your normal anti-malware procedures. You can use it to bypass code obfuscation, code encryption. If your malware payload is encrypted, it's only encrypted when it's on the disk. It's not encrypted when it's being run, because that doesn't work. So you can pull, and I have used that once or twice, of just running things and then using recall to pull the running malware, and suddenly it's reverse engineerable. You also don't have much reliance on the OS. You're not using API calls to fetch your stuff from Registry. You're not using API calls to fetch files. So you're not relying on anything that could be subverted by rootkit, hooking API calls and so on. So what is fileless malware? It's basically malware which doesn't exist on disk. It's something where it doesn't drop any files to the backing hard drive at all. In theory, the term, I think, gets a little bit misused at times to refer to things which really just do a very good job of hiding themselves. But it's also called memory-only malware, or for some reason, I have no idea why they came up with this one, none-malware. It mostly refers to registry-based, where their persistence mechanism uses the registry rather than files. Because of that, it relies on Windows functions like the management instrumentation and Windows PowerShell to actually run any commands. There's a huge amount of power in those, as we'll see shortly. So we'll just have a look at a couple of examples of fileless malware. Powerlix was one of the sort of forerunners of it. Probably not the first, but the first that actually was widely successful. It was a follow-up to a piece of malware that had been around for a while, but it went fileless in 2014, switching from using your standard rootkit, dropping files on the disk and then hooking calls to hide them and stop the OS or the user discovering them, to actually just being a registry-based threat. It has a persistence mechanism which relies on a second process it injects into an existing process, a thread it injects into an existing process, which it calls the watchdog thread. And that basically just loops constantly, making sure that its registry keys exist, haven't been altered, and it also messes around with the access permissions in the registry so that a normal user can't even see those keys are there or read them. And it also uses special characters in the registry key. Seems stupid, but it uses special characters in the registry key, which actually stops it being detected by an awful lot of automated tools and so on that you might use in analysis. They just don't detect the names of them. It uses a program called run32, rundll32.exe, which is just a Windows API or Windows program to run and load modules. So you can run that to load your own DLLs and so on. I don't know how clear that is at the back, but that is taken from a report on the malware by, I think, Sophos, this one was. And you can see it's got two registry keys colored. The first one is the main command, which runs JavaScript code. That's a surprisingly common theme, by the way. You might not expect JavaScript to be used in, well, malware running in your registry, but that is actually surprisingly common to see run DLL32 using JavaScript code. It runs something which will get that second key, the A key, which is a encrypted or encoded PowerShell payload, which contains that watchdog process to protect its registry keys and make sure it can persist beyond computer restarts. Phase or phasebot is another example. Again, it was a sort of mutation of an old virus called SolarBot, which was an old rootkit again. That SolarBot was a fairly widespread piece of malware back in 2012-13, I believe. This one was slightly different in that it didn't bin its rootkit capabilities when it switched. It added fileless. So it would, at runtime, possibly go over this here. At runtime, it would look at whether or not PowerShell's installed and whether or not .NET 3.5 are running on the host machine. If they are, then it'll go fileless, drop registry keys, and use PowerShell to carry out its functions. If they're not available, then it just switches back to its old rootkit functionality and drops its files onto the disk and installs hooks to hide them. Again, as I say, it is heavily reliant on PowerShell, and this one included a module loader so that the malware author could customize the malware in situ. Again, just like the last one, the registry key, these are the registry keys for it. This one uses three. The RC encoded 34 are your payloads, just encoded for 32 and 64-bit machines, and then there's a JavaScript key which actually has the PowerShell script to decrypt and execute the payloads. This also had encrypted command and control as part, just in that one, the commands included there, it was able to carry out encrypted command and control and customized modules. The DNC hack, I couldn't really go past without mentioning something about this, without getting into the politics and the mess around this. There were supposedly two actors acting completely independently, Cozy Bear and Fancy Bear. Cozy Bear seems to have used a PowerShell backdoor, gaining persistence through the management instrumentation again, which are just a series of tools Windows exposes to allow scripting of management tasks, basically. There's the actual PowerShell command that CrowdStrike pulled out for Cozy Bear. And again, I've shortened the encoded command. That goes on for several hundred lines. It's a huge, huge command, but the depth, for one-line command, the depth of control that gives is quite impressive. Fancy Bear, again, slightly different tactic, but the same kind of thing. You see, again, run DLL32 appearing here, loading his own custom DLL. So what can we look for, based on that, what can we look for in memory that might actually be valid to us? First of all, you've got the registry keys, obviously. You've got permissions, as I mentioned with the PowerLicks. It messes with the registry permissions to try and make them harder to find. So if you can find keys that have weird permission tokens on them, weird security tokens, then you can start. You've got to start for something. Suspicious threads. If we're looking at system processes and they've got threads that shouldn't be there or threads which are sort of hidden from your end user, then again you've got something suspicious to start picking at. You can extend those a little bit, and this is just what I can come up with. Might be missing a few things, but you can also extend these to include JavaScript, and there shouldn't be many cases that I can think of where you have JavaScript in a PowerShell command legitimately. Maybe I stand to be corrected on that one. You can look for commonly exploited EXEs. You're going to hit a lot of false positives with that because they're there for a purpose and they're used, but it can maybe be a start. You can look for oddities in legitimate processes. So you've got known strings, you've got permissions, parents, like parent processes and so on. Again, it's the same kind of thing as you would look at in normal malware analysis, but you've got a higher level of access than you do if you're relying on the Windows operating system. Keywords as well, because I mean, we're just searching through memory. You can search for anything you like. So just move on to looking at Windows memory in general. So I'm going to be looking at, in this, mainly Windows memory itself for the operating system rather than user land. So when you're looking at memory access, you have the ring system, ring 1 to ring 3, ring 0 to ring 3. I think I got this right way around. Ring 0 is the most privileged and ring 3 is the least, although I stand to be, I think I might be wrong on that one. At ring 0, you have kernel level access. You can access the kernel memory pools, and at ring 3, you can access the user level, but you cannot modify or read stuff that is within that ring 0 kernel pool. So what I'm looking at here is the kernel. I'm interested in what is Windows storing, not what is the user storing, because this is slightly more usable. There's slightly less obstructions to getting information from this. So when you first start up Windows, the memory manager allocates 2 pools, simplifying things a little bit. Non-paged and paged. They're fairly self-explanatory. The non-paged pool will always be in memory. It's never switched, never moved out. It's used for critical things like drivers and some aspects of the kernel. The paged pool, again, works in, by default, 4 kilobyte memory pages, and they can be switched out to the backing disk as memory demands. So if they're not used for a while and memory starts running out, then it'll page sections of this out to the backing storage. They technically count as still memory, they can be pulled back, but they're not available on RAM. Yeah, I think that covers. Oh yeah, for performance purposes, single processor systems generally have 3 paged pools, and multiprocessors, pretty much everything we have now, will have 5. That's according to MSDN. As far as I know, that's relevant to Windows 10. So executive objects are basically objects, but in kernel memory. They're objects like int, file handles, pretty much anything that you'd normally have in a program, but they are managed by the Windows memory manager. So or the Windows object manager, sorry. So they are given special headers within the kernel pools to allow Windows to handle them more easily. So they have extra headers that you'd normally have, which makes them useful. I've listed a few types that you might find there which are useful. They're fairly self-explanatory. Token is your SID or security ID token. Key is registry keys that are open in memory. Mutants are mutual exclusions or mutexes. I think the other ones are fairly self-explanatory. The thing about executive objects is they always have an object header. I actually missed one out here. They always have a pool header, an object header, and then optional headers depending on the kind of object they are. So you've got a nice set structure that you can be looking for to try and profile. I'll go into a bit more detail on those in a minute. When a driver, say, tries to allocate memory in the kernel pools, it doesn't have to, but it should assign a pool tag. These are just 4-byte values which go into part of the pool header, which is the very first thing you find on any object. They are meant to define the caller. So they're a debugging tool to enable you to trace any issue back to the calling process. So if you're getting a memory leak, for instance, the idea is that you can find what is causing it and trace that, the allocation that is the problem, and trace it back to the calling process and try and use that for debugging purposes. As such, they're not critical. They can be altered, they can be changed, they can be misused, most commonly just misused. They don't even have to be allocated. But they're generally used by most systems and are quite a good classification tool. So here, when you install the Windows debugging tools or WinDBG, you get a pooltag.txt file in the install directory, which just shows all the pool tags that are being used by your system. So I just put a quick screenshot of the one from my laptop, just as an example. You can see, for instance, NVIDIA uses multiple tags, and that list actually goes on for a long way up above. So it's not bound to a manufacturer, it's not bound to a vendor, it's just a classification thing, it's a debugging tool. So if you were looking at any aspect of a certain aspect of the NVIDIA driver when you're trying to debug, you can trace it down to quite a narrow tool, but they can be useful for other things too, as we will go over. The whole picture changes a bit when you start looking at big pools. Big is slightly odd because it's only 4 kilobytes. So in modern operating systems, that covers quite a bit. And again, 4 kilobytes is a page in memory. So anything over one single page will be allocated out of the big page pool rather than your normal kernel pools. That just means it's intended for speed and efficiency, so that the operating system's not trying to track multiple tables or storing similar data. The difference with this, which makes it harder for our purposes, is you lose the pool headers, which have the pool tags in them. Allocations are managed within separate track tables. So on the left, you've got a normal allocation where you have your pool header. You'd then have it within that allocation, object header, optional headers, data. Whereas you lose that if it becomes big pools. So that loses some information and makes it a little bit harder to pull anything out. Now I'll come back round to object headers, which in hindsight I should possibly have done a little bit earlier. These, as I say, precede every allocation. It's quite a large structure, but the key members I've highlighted there, the ones that we can most use. Pointer count references how many times this is actually being referenced by anything on the machine. So anything that has addresses into this library or DLL or whatever are referenced there. Handle count, similarly, anything which has an open handle to this file, anything that has the file or key open or wants to write to it, that will be stored. That handle count affects whether or not something will be paged out. If there are still open handles to some data, then it'll be unlikely to be paged out of memory or deleted. As with a lot of this, I'm trying to keep it sort of understandable on slides, but these tend to go down a hierarchy. So type index is an index into another array of different data types, which you then follow down the tree until you get to your actual reference of what type of object it is. But there are a couple of tables in between, and that's true of quite a few of these kind of things. Unfortunately, it makes it quite a lot harder to step through them. Info mask is interesting because it tells you exactly which optional headers should be present. So if we find an object header, you can read the info mask and know exactly which headers you should expect to find after it and which ones you need to be parsing. And then security is useful for finding out what access rights and who is responsible for allocating this object. Processes follow a similar pattern. You've got a structure, the e-process structure. There's a diagram defining it there that I took out of the art of memory forensics. You can see the process actually includes quite a lot of stuff. You've got your handle tables to anything it's trying to load, any files it's trying to load. You've got your threads, which are useful for us. Loaded modules, again, your DLLs. which the process is making use of, and your security IDs and so on. These structures are linked to all other processes on the computer. So when you look at your task manager process listing, what that is doing is going to the kernel debugging sec data block, picking out the address for the first process structure, going to that structure, reading the relevant information, and then pulling out of that eProcess the F-link value to point to the next process structure and so on, and it just goes down the list, enumerating every process and showing them on the screen. So you've got this doubly linked list. There's an F-link for the next one and a B-link for the previous, and a B-link for the previous process. Yeah, I got a bit ahead of myself there. The problem with that is that anything in a header is editable, and the F-link and B-link values, again, aren't critical to a process actually running. So that is fine for nice, quick, your task manager kind of view of processes, but it is possible to hide anything from that. If the link is broken and an F-link passes over one process, it won't pay any attention to the fact that that process is there, which is one advantage of memory scanning, in that we're just looking for headers, we're looking for signatures of a process rather than relying on the Windows APIs to find them for us. Say the simplest way of finding these is just scanning for eProcess headers. But you've also got a couple of alternate process listings down there. You can scan for threads instead of headers and then work backwards to their parent, which can be a useful sort of double check aspect, or you've got handle tables. The OS keeps track of open handles on the system in a few places. I think the csrss.exe module keeps track of one. I can't remember what it stands for. And you can enumerate those to see what files are owned by what processes, and sort of work back that way as well, which can be slightly more reliable than your basic F-link, B-link, double link list. So following on from that, you've got your threads, which are just one step down. Each of those sort of thread sections on the right will be a pointer to an eThread process, an eThread object, sorry. Again, same kind of thing as processes. You can just scan for the eThread header. It has set patterns, and then trace back to the parent process if you want to try and find out ownership. You can also, or you can go the other way around, try and locate threads by enumerating everything that belongs to a process. This kind of thing can be useful, as I say, for a malware example, which, like that one with the watchdog, Powerlix. That one injects a thread into an existing process. I think that one uses a system process. So if you've got a mysterious thread running under system which shouldn't be there, then you've got, again, a clue that something malicious is going on. There was some interesting work carried out a few years ago looking at signatures for machines. How can we use memory data to perform malware analysis, but quickly? Because that's going to be one of the problems of this. And what they were doing was basically stopping processes until the computer crashed. So they would stop process. If it wasn't critical, then fine. If the computer crashed, they were classifying it as a critical process and storing data about it. And what they did through that was build up a signature of the most valuable of what a system needs to run. And they could then use that to basically do signature checking against the contents of memory. And that turned out to be quite effective from what I saw. Quite complex, but that seemed to be quite an effective threat. So this is a basic form of that. You can look at what sort of signature should the system process have, why are there 3 extra threads? Again, memory analysis can be useful here because, as I say, you can't necessarily trust the Windows systems for finding these things yourself. So the registry side of things is slightly more complex than the others, as usual when you try and look at the data structures for registry. It does have the advantage from this point of view that it's always handled by the OS. If you write a driver that opens a registry key, you make a request to the OS to open the key, and it will be opened within the kernel space, and you will have a reference to it if you're in user mode, and so on. So it's always handled by the same memory management object component in the Windows kernel. So you've got reliable pool tags. You're not relying on a third-party developer to have actually used the correct 4-byte tag when they're writing these things. The problem you do have is that registry keys are not always used very often. So you can find that you get a very broken image of the registry from memory. When you open a key, the whole registry is not copied into memory and just the one key you want used. It just copies the hive that you're accessing, the sort of parent block of the registry that you're accessing. So it doesn't give a very complete picture all the time, but this can still be, if you get lucky, there can be a huge amount of information there to pull out. If you're trying to find registry hives, again, you can scan your memory pools for the tags. You then have to check that it's valid, because you can get leftover hives which are no longer up to date. You have to check it's valid using the signature member, which is part of the header. And then you can use the hive list, which is another array within the header, to try and locate all other hives that might be in memory. So you can, if you find one, you can extrapolate to all current hives, but as I say, it can be quite a broken picture, and experimenting with this has been quite tricky compared to some of the other things. So just as an overview, it follows quite a common concept. You've got the hive bins, which store actual block of registry data, and then each of those is broken down into the key value pairs that you'll actually see. So you've got pointers to another table which actually contains data. Going back to the last one, this CM hive structure is covers the left hand, while the H hive covers the right hand side. So they're the two different structures which link to each other and represent the registry. And yeah, registry operations are always carried out by the configuration manager. This handles all aspects of registry operations and address translation. That's handled separately from the normal address translation that you'd see in the OS. So how do we find any of this? Well, the first thing you need is basically kernel level access to memory. If you are just trying to read this with a Python script, then you're going to find that A, you're in user mode or ring 3, and you don't have access to anything other than your address space for that program. So you need a kernel driver, basically. I use WinPMem by the recall guys as a signed driver. You can get around to an extent using Windows APIs. You can get a surprising amount of information by going to the Windows APIs rather than to memory. But as I mentioned before, you get a lot of issues. When we're looking at malware, you potentially fall foul of the actual anti-forensics techniques which we're trying to avoid. So you can get some value out of it, but it's not that useful. So pool scanning is the most obvious one. Pool scanning is just what it sounds like. You've got those memory pools that are allocated from address range 0 to 20,000, and you just scan through it as though it's raw data. You read it out, scan through it, and parse it. You're looking for whatever you're trying to find, pool tags, header tags, whatever. It does, as I mentioned, it has the advantage that it bypasses a lot of anti-forensics techniques, and you can search for anything you want. I mean, you can just type in a string and search the memory for it, which is helpful and confusing at times. The cons are, it's big. On this, I'm finding generally the none-paged pool can be several gigabytes or larger, and you're basically trying to read a several gigabyte file, parse it, and deal with it in a reasonable length of time. So my dissertation project originally was aimed at trying to create a tool for dynamic analysis for malware. And I've had to sort of scrap that idea because using pool scanning, I'm not able to do it in a reasonable length of time. If you're trying to look at malware, you need it to be checking every sort of few seconds, where it's taking 10 minutes for me to get a run through memory. So it does have problems with that, but for forensics points of view, it works well. For live analysis, not so much so. It puts all the weight of parsing and analysis onto the person doing the scanning or the person writing the scanner as well. You've got no help from the OS, you've just got a block of data, ASLRs in effect, you've got paging and so on. So all the weight of understanding what is going on falls on you rather than getting any help from the operating system. There's also a large chance of false positives because you're just scanning for text. Chances are that those tags are going to appear accidentally anyway. So we'll cover how you can try and reduce that later. Tag scanning is an extension of pool tag, where you're looking for the pool scanning, where you're looking for the pool tags. Again, as I mentioned, not always reliable and not always there. They can vary regularly, so you have to keep your scanner up to date, and they can be manipulated maliciously. You can choose what you want your tag to be. When you ask for an allocation within the kernel pools, I think the function's x allocate with tag, and the tag is not a required parameter, so you can just leave them empty. And as I mentioned, large allocations don't have pool tags, so as soon as you hit anything over than pages, anything over than 4 kilobyte allocations, this goes out the window anyway. But it does have uses for certain scenarios. How can you reduce false positives? Basically, the answer to that is use as much data as you can. With the object headers and so on, you have got a nice big rigid structure where you can say fairly safely what you should be able to find at byte or offset 4, offset 8, and so on. So once you find that first pool tag or that first header, you have to then start working your way down that list and try and check, well, is this an object? Is that field where it should be? Is that field where it should be? And try and pull in as much information as you can to take that out and reduce that uncertainty. You can make use of tracking tables. For instance, the page allocations are tracked by the management module and stored in tables. If you can locate those, and some of them are fairly reliably located in the kernel address space. They can serve as a reference to get you started and as a double check when you're trying to find things. So is this one meant to be there? You can use it to get you to the first process to then start following links from there and so on. So they can be quite a useful reference. And just follow pointers. If you've found one already that is 100% a structure that you're looking for, then use the information in that. You can follow links from it, you follow pointers, and pull out more information from that. The key is just try and get the context you're in. As I say, with pool scanning, it doesn't give you much help, but you just got to try and work out yourself what context you're in and try and pull that mess of hex into some kind of, or mess of bytes into some kind of understandable format. So just getting towards the end, the major issue, ignoring what I looked at with pool scanning and so on, what are the issues with running live analysis? As I mentioned, forensics is a very different tool, a very different proposition. You don't have to worry about the fact that you're running on the machine that you're testing. You don't have to worry about memory changing whilst you're working on it, which is a problem here. For instance, if you're trying to follow pointers down the line, by the time you get to the end of the line, that bit could have been paged out of memory. So you do have risks while you're running it live on a machine. So if you don't use it, you lose it. Paging means that, paging and the fact it's volatile, means that if something's not being used or is finished, then it's moved. So it's not a constant environment. The very act of running analysis changes what you're looking at. You're running a program on the machine you're investigating, and that's causing stuff to be loaded into memory, it's causing paging to take place. So just the very act of analysis can change stuff. And of course you've got the performance impact. As I say, with my basic attempts at doing this with Python and WinPMem, I'm taking up to 10 minutes to make a run, and it's, well, eating up like 90% of my ability to write to memory. So it's fairly performance intensive. So what I'm currently working on for the dissertation side of things is how to reduce that and how to make it practical in the real world. So if anyone has experience or advice on that, I'd love to hear from you. So that brings me to the end. I don't think I've anything else to cover, so does anyone have any questions or advice or anything? Nope. Okay, well, I'll be at the pub later, and you can catch me on Twitter if anyone wants to talk.